Hi everyone, this series of videos is going to take you through the next lesson in the new packet, which begins on page 6. As you may remember, the previous lesson took you through pages 2 through 5 in the new packet, which can be found in the learning plan. This week's lessons are all in pages 6 through 11, which is a new chunk of the new packet. And I'll remind you, just as I reminded you in the previous lesson, that this is not a packet that you physically received when we were still in-person classes. Unfortunately, your only way to access this packet is through the learning plan. You'll have to open the PDF, and if you have a printer at home, print the pages of the packet so that you can follow along. If you don't have access to a printer, the best option is to simply keep the pages open on a screen of some sort and follow along with the problems just using a regular piece of scratch paper to write anything down. I do suggest that you try to interact with the packet problems as much as possible though, as opposed to just listening and watching this video without writing anything yourself, because I think to mimic the classroom experience, the best way is to kind of maintain the routines that we've always had, which is for me to go over something, for you to try it on your own, and that sort of back and forth dynamic that really helps us engage with the material and not just sort of passively tune out as we listen to a boring voice that you can't even see. So that's why I do recommend, if you haven't yet, making sure that you have access to these pages and making sure that you take the time to use the pages the same way we would if we were in-person class situations. Now, pages 6 through 11 are going to kind of piggyback on an idea that we saw in the previous chapter, chapter 4, which was the fundamental theorem of calculus. There's a section at the top of page 6 here that just recaps what the fundamental theorem of calculus was all about. And while it's not necessary that you go back to chapter 4 and redo a lot of things with the fundamental theorem, it might be worth reminding yourself of what it is. Simply because anything that is so boldly named as the fundamental theorem of calculus is probably pretty important, or dare I say, fundamental in its importance. So when you think about the fundamental theorem, hopefully the one thing that comes to mind, if anything, is the fact that the fundamental theorem is the place where we explicitly say that the antiderivative of something is the same as, or is not the same. The antiderivative of something is the process of finding an integral or finding an antiderivative, starting with the derivative and working backwards, plugging in the two limits and subtracting those two limits. That's basically what the fundamental theorem says. It says, hey, if you have to do an integral and you have to do it with calculus, do that process. Take the antiderivative, plug in b, plug in a, and subtract the results. Now, there's a lot of theory behind the fundamental theorem that we don't really go over in these online settings because it's pretty deep, it's pretty abstract, and if you Google it, you'll find lots of different professors making videos who actually go in depth about why the fundamental theorem works, and they prove it with all sorts of abstraction. I'm not going to go that deep with it, but if you want to self-search, just Google the phrase fundamental theorem of calculus. You'll find lots of info. For now, I'm just going to try to focus on the most practical bits of the fundamental theorem, and that's really what you need to know in order to solve problems. For now, the fundamental theorem as we understand it is basically a two-step process. Take an antiderivative and plug in to evaluate with those limits a and b. That's basically what you need to know about the fundamental theorem. Today's lesson is going to expand upon that a little bit and to bring up what I call a weird hypothetical situation. And that's what you're going to get into in this middle section where it says a note about notation. If at any point you want to take some time to really read the text of these page 6 paragraphs, I recommend that you pause the video or even stop the video and come back to it later so that you have some time to really chew on these ideas. Because the text here is meant to kind of help expand upon some of the things I'm talking about, and I'm not reading the text word for word when I make these videos. So if at any time you need more context or more information, reading the page might help round things out. In any case, I'm kind of dealing with this first section, reminder about the fundamental theorem, but specifically the question posed in this second paragraph. What if the integral didn't have a defined a and b? What if we didn't know where the integral was supposed to start or stop? What if those were unknown? We already have to deal with the fact that x is unknown. X is kind of our variable, so to speak. But what if we had another unknown quantity? What if we didn't know where to start? What if we didn't know where to stop? Maybe we don't know both. That's what the second fundamental theorem is meant to expand upon and clarify. Now, this section is going to be kind of heavy on notation, so the middle bit here about notation is definitely worth a deep dive. Again, if you need to pause the video so that you have full attention for this, this would be a good time to do that, because the notation involved in the fundamental theorem can be a little bit unique in ways that might not be super obvious. Really, we're going to be dealing with this notation that you'll see on the right-hand side, the definite integral as a function of x, and you'll see some subtle differences in this new notation compared to the way we were seeing problems before. Before, we were typically dealing with f of x dx as kind of a way of saying, hey, we have this antiderivative that we have to do. We know that we're dealing with a function that was in terms of x because this dx, this implicit notation, is saying, hey, yeah, that was x. That was our variable. We know that. When we're dealing with the fundamental theorem problems, or these new abstract situations, you're going to probably notice pretty quickly that the variable becomes t, and it might seem like a peculiar choice, like, wait, are we doing time problems? T is actually called a dummy variable. And there's a bit about this at the bottom of the notation section. A dummy variable is actually kind of a temporary variable. It's a luxury that mathematicians use, and granted, it's kind of an advanced move. It's sort of a level up move for real. But it's a move that mathematicians make when they know that that variable is going to end up disappearing anyway. So it's kind of like a little placeholder. For now, all you need to know is, yes, t is going to be the variable in these problems. No, it doesn't really matter. So it's one of those things that you should notice, but not fixate on. The x that you're used to seeing is still part of these problems. X is now what we're going to call the upper limit. X is now going to be one of the things that after we do the antiderivative, we plug in, which seems peculiar, I'm sure. Like, why isn't x the main variable and why isn't the dummy variable one of these things? Those are things that we'll get into eventually, but for now, just notice that. Notice that the problem itself is going to be in terms of t, and that x is another variable that is also part of the problem. So there are going to be two variables to kind of deal with here, and all you need to kind of pay attention to is the fact that there are two. You don't have to worry about the choices as to which is which. This is not a decision you'll ever have to pay attention to for yourself. It's just worth noticing. Now, again, I'm going to go over just the details and the salient points that you need for the problems in these videos, but if you want to take some time to really dig deeper into the notation, this is a good section to read in more depth. The last thing I'll have you notice before we really make sure that we can start these problems is the fact that in fundamental theorem questions, you're going to deal with this big F and little f juxtaposition. We actually saw that before we left for these online classes. The last week we're in class together, we talked about the big F, little f very, very briefly. This section is really where the big F, little f discrepancy is going to come in and make a bigger difference. So just pay attention to it. It's unfortunate that they're both called F, so you'll hear me refer to them as big F and little f, so as to distinguish which one is which. The general rule of thumb is that little f is a derivative. Little f is that thing that they gave us in the integral that was saying, hey, we took a derivative of something in terms of t, see if you can figure out what the original one was. That's what little f is. And big F is the antiderivative. So it's kind of an inverse relationship. Little f is the derivative, big F is the antiderivative, and we're going to go back and forth between them. Now, all of that was kind of a lot to digest. That's a lot of scene setting. That's a lot of information to process. That's a lot of information to think about. And yet I haven't given you any problems to do. So between now and the time you start the next video, just make sure that you have a decent handle on the notation of integrals, what the different parts mean, and maybe even preview what's to come in the next videos and the next pages, so you have an idea of what exactly we're going to be trying to do here. On the subsequent pages and in the subsequent videos in this playlist, we're going to walk through some specific examples, but I just want to make sure you know what you're getting into first. So before you start the next video, take some time to flip ahead, take some time to read all of the text here if you feel like your head is a little bit swimming, and then start the video that explains example 1 when you feel like you're ready to absorb more information.